Welcome to AI Paperslop. Today, we are looking at the Stable Audio 3 technical report by Zach Evans and the team at Stability AI. And let's just get straight to the core insight for those of you building generative models.
Yeah, they really dropped a massive one on us this time.
They did. So the team just released a new family of open-weight latent diffusion models. We are talking small, medium, and large variants that are capable of variable length audio generation up to 6 minutes and 20 seconds.
Natively, too, which is just huge.
Right, natively.
Yeah.
And it operates on this completely novel Semantic-Acoustic autoencoder that pulls off an absolutely massive 40-96 times downsampling ratio.
Which is kind of unheard of for high-fidelity audio.
Exactly. And through a 3-stage training pipeline that culminates in adversarial post-training, they've distilled inference down to just 8 self-correcting ping-pong sampling steps.
And no classifier-free guidance needed, 0 CFG at inference.
None at all. The result is state-of-the-art music and sound effect generation that runs in under 2 seconds on an H200, and it even scales down smoothly to consumer GPUs and MacBook Pros.
Yeah.
So, okay, let's unpack this, because for those of you building these models, this paper is just a goldmine of architectural tricks.
Oh, absolutely. I mean, from handling variable length diffusion natively to the novel sampling pipeline, it's a masterclass. But to understand how they do it, we really have to look at the bottleneck first.
Right, achieving that 40-96 times compression.
Yeah, because to generate long-form audio quickly, you first have to drastically compress the waveform. Like prior audio diffusion models typically hit a wall at maybe 124 times downsampling or, 2048 times if they push it.
But Stable Audio 3 pushes it to 40-96.
Right, and they do this using what they call the same autoencoder, the semantically aligned music autoencoder.
Okay, wait. Compressing audio by 40-96 times usually just destroys high-frequency fidelity. I mean, it's like taking a high-res photo, crushing it into a tiny pixel art thumbnail, and then just expecting the AI to guess the microscopic textures. How does this not just sound like underwater garbage?
That is the exact problem they had to solve. So they start by reshaping the 44.1 kilohertz stereo audio into patches. That gives them a 256 times downsampling right out of the gate.
Okay, sure.
But then they use transformer resampling blocks, or TRBs, for another 16 times compression.
So that gets us the rest of the way.
Yeah, exactly. Resulting in these 256-dimensional latents running at about 10.76 hertz. And crucially, they don't use standard VAE regularization here.
Right, I noticed that. They use a soft normalization bottleneck instead.
Yeah, exactly. But back to your fidelity question, how it doesn't sound like underwater garbage. They built this highly complex loss landscape. It's not just a simple reconstruction loss.
Yeah, they use a multi-resolution STFT, right? A short-time Fourier transform.
Right, and they compute that independently on the mid and side channels as well as the left and right channels to preserve the stereo imaging. But then they add a relativistic Jan loss.
Which forces the audio to actually sound perceptually real to the human ear.
Precisely. And they pair that with semantic regression. So they explicitly force the model to predict chroma, which is the harmonic content, and interval level differences.
So that keeps the left-right ear balance completely intact.
Yeah. But what's fascinating here is the diffusion alignment loss. The autoencoder isn't just trained to reconstruct audio.
Oh, this is the part where they train a tiny diffusion model jointly, right?
Yes. They train a tiny 4-layer diffusion transformer jointly on the latent space while they are training the encoder, so it forces gradients all the way back through the encoder.
That is so clever. So they are ensuring the latent geometry is explicitly friendly for the downstream diffusion process later.
Exactly. It preserves both acoustic fidelity and semantic structure, and they lock in that semantic alignment with a contrastive loss using a frozen T5 Gemma text encoder.
Wow. And they built 2 variants of this autoencoder, right?
Yeah, the same S, which is 108 million parameters for their small model, and the same L, which is 852 million for the medium and large models.
Okay, so the audio is tightly compressed into this optimal latent space. But how do we actually model it? Because the major headache in audio diffusion is fixed-length padding waste.
Oh, it's a massive waste of compute. Standard transformers want fixed lengths.
Right. If I want a quick, 2-second drum fill, I don't want the model computing 6 minutes of empty silence around it.
Exactly. So Stable Audio 3 solves this by handling variable length inference natively. But let's look at the model sizes first to ground this.
Here.
The small model is 459 million parameters, and that handles up to 2 minutes of audio. The medium is 1.4 billion, and the large is 2.7 billion. Both of those can do up to 6 minutes and 20 seconds.
And the architecture is a pre-norm transformer.
Right. And they inject the diffusion time step and the target duration via adaptive layer normalization, specifically ETL and single.
And then the text prompt from T5 Gemma gets injected via cross-attention.
Yes, alongside the duration again. And they stabilize that cross-attention using QK-RMS norms so the logits don't blow up.
They also prepend 64 learned-in-memory embeddings to act as a global memory buffer.
Yeah, that's a nice touch. And for the medium and large models, they use differential attention.
Oh, where they subtract 2 independent attention maps to cancel out the noise. I love that technique.
It's incredibly stable. But to get back to the variable length training solution you brought up, the way they handle batches is really smart.
Right, because in a single batch, you might have a 10-second clip and a 5-minute clip.
Exactly. So the shorter sequences are right-padded to match the longest one in the batch, but they are completely masked out of the loss and the self-attention using variable length flash attention.
So the model literally just ignores the padding. It doesn't waste capacity learning silence.
Right. But here's where it gets really interesting for anyone working on sequence modeling. They introduce this length-dependent noise schedule shift.
Okay, yeah, I love this part. If you pour the exact same amount of ink on a postcard versus a massive billboard, the billboard still has plenty of readable space.
That's a perfect analogy. Longer sequences have way more internal correlation.
Right, so a fixed noise schedule will essentially undernoise your long sequences. To corrupt the billboard equally, you need way more ink.
Exactly. So they use a logistic shift during training. It dynamically pushes longer sequences toward higher noise levels.
That is a brilliant insight. And they also do silence augmentation, right?
Yeah, appending exponential random lengths of silence to the signal. That way the model learns to naturally fade out a song, rather than just abruptly cutting it off at the end of the tensor.
Okay, so the architecture is dialed in. Now let's get into how they actually trained this.
Yeah.
Because standard diffusion takes dozens or hundreds of steps.
Which is just too slow for real-time creative workflows.
Way too slow. So they use a highly specific 3-stage training pipeline. Stage 1 is flow matching pre-training.
Right, which trains a velocity field mapping noise to data. And they use mini-batch optimal transport coupling here.
To straighten the trajectories, right?
Yeah, it essentially pairs the noise with the closest data sample in the batch, so the model isn't learning these wildly tangled paths, and they use truncated logit normal time step sampling.
So they focus the training compute on the intermediate to high noise levels where the actual heavy lifting is done.
Exactly. Then comes stage 2, which is the distillation warm-up.
This is where they take a frozen teacher model, right?
Yeah, a frozen copy of the flow matching model. The teacher generates these clean 15-step ODE trajectories, and the student model learns to predict the final denoise output in a single step.
Using a mean squared error loss. But MSE has a massive flaw in generative modeling.
It really does. It causes regression to the mean. If the student model is unsure about a high-frequency detail, it just averages everything out to play it safe.
Right. It's like the distillation stage teaches the model to speed run a maze by just crashing straight through the drywall. It gets to the end really fast, but it leaves the maze an absolute mess.
That is exactly what happens. The audio sounds blurry and washed out, so they introduce stage 3 adversarial post-training.
The inspector that comes in and forces you to make the maze run look elegant and precise.
Right. If we connect this to the bigger picture, this is why adversarial post-training is superior to standard consistency distillation. You aren't just memorizing the teacher's path anymore.
Because they ditch the teacher entirely.
Exactly. They bring in a relativistic discriminator that operates at a completely decoupled noise level. It compares the student's one-step prediction directly against real, uncompressed data.
So it forces the student to actually recover that high-frequency sharpness.
Yeah, it frees the model from the teacher's quality ceiling. And they also add 2 more losses here to anchor the text alignment.
Right, the contrastive loss, where they shuffle the text prompts to force the discriminator to actually check if the audio matches the text.
And the CLAP loss. But they don't just use standard cosine similarity for the CLAP loss. They minimize the squared geodesic distance on a unit hypersphere.
Okay, let's translate that for the listener. Standard cosine similarity just measures the straight line angle. But if the audio and text are totally misaligned, that angle flattens out and the gradient essentially dies.
The vanishing gradient problem, yeah.
But squared geodesic distance literally calculates the walking path across the surface of that hypersphere globe.
Exactly. It ensures the model always has a strong, consistent learning signal no matter how far apart the prompt and the audio currently are.
That is just brilliant engineering. So with all of that training, how does this actually run in production? I mean, technically the model can generate in one step now, right?
It can, but the paper admits that mapping pure noise to clean audio in one massive jump still leaves some slight artifacts.
So what's the fix?
Ping-pong sampling. Instead of one step, they use 8 steps. It alternates between denoising to an estimate and then stochastically renoising it at a lower time step.
Oh, wow. Why does that beat a standard ODE solver like Euler or DPM?
Because it is inherently self-correcting. If an ODE solver makes a bad estimate on step 1, it just mathematically propagates that error all the way to the end. The damage is permanently done.
Right, but with ping-pong sampling, if the first estimate is a bit off, that renoising step gives it a fresh, slightly noisy state.
Exactly. It gives the model a chance to look at the signal again and fix its own mistake.
That is a huge paradigm shift. And another crazy thing about inference here, no CFG.
Right. 0 classifier-free guidance, because they baked the CFG into the teacher trajectories during the distillation warm-up and then enforced it with the CLP loss.
Which instantly halves the compute requirement. You don't have to run that unconditional forward pass anymore.
It's a massive speed up. And it natively supports inpainting, too. Single segment, multi-segment, causal continuation.
And they do that by concatenating a binary mask and the masked reference audio into a local additive conditioning signal.
Via a 0 initialized MLP, yeah. So they can fine-tune it for inpainting without shattering the pre-trained weights.
Okay, so the million-dollar question. What does this actually mean for your VRAM limits?
The hardware requirements are honestly fantastic. The small model uses only 2.4 gigabytes of peak VRAM to generate 120 seconds of audio.
Wait, 2.4 gigs?
Yeah. And the medium model uses 6.5 gigabytes for the full 6-minute and 20-second generation. So it easily runs on an RTX 3050 or 4060.
That is wild. And what about Apple's silicon?
Using Core ML on a MacBook Pro M4 CPU, the small model generates 120 seconds in just 3 seconds.
Incredible.
And if you have an H200 running TensorArt, it generates the full 6 minutes of audio in under 1 second.
Under 1 second for 6 minutes of audio. That is just absurd. So, to synthesize this massive amount of engineering we've covered, this paper is essentially a masterclass in stacking efficiency techniques.
It really is.
You've got the Semantic-Acoustic Autoencoder, variable length flash attention, optimal transport flow matching, adversarial post-training, and that ping-pong sampling trick.
And they didn't sacrifice quality either. The Frichet audio distance and CLA P-scores actively beat baselines like Stable Audio 2.5, ACSAP 1.5, and Whoosh Flow.
It's an incredible achievement.
It really is. And this raises an important question that I kind of want the listeners to think about. The ping-pong sampling mechanism proves that a little bit of stochastic backtracking is actually better at fixing single-step errors than deterministic ODE solvers.
Right.
So for those of you working in video or image diffusion, could intentionally injecting renoising steps into your distilled models be the missing key? Like, could that help you escape the blurry artifacts of one-step generation? Think about how you might apply that to your own pipelines.
That is a deeply fascinating thread to pull on. It turns out that sometimes taking a half step back really is the best way to move forward cleanly. Well, thank you for joining us on this deep dive into Stable Audio 3. We'll catch you next time on AI Paper Slop.